We're going to do an analysis of a crumple zone, similar to your project, and this is the guided practice. So I've got my my egg here, my EPD, and here's the information given in the problem. It says you design your egg protection device. When you weigh it, you find that the device has a mass of 100 grams. And you drop your 60-gram egg, so you need your 60-gram egg in there also. 2 meters from the floor. So that's where I have the bottom, right at 2 meters. So this is 2 meters. The egg container has dimensions of 10 centimeters wide. So that would be this distance, the width. 10 centimeters deep, that's back this way. I don't have that dimension shown. And 15 high. So that's the whole egg container. This one here is 15 centimeters high. The crumple zone dimensions are 10 by 10 by 15 also. So this dimension is also 15 centimeters. So those are important, that's important information. So then let's start answering the questions. Question 1. Use kinematics to find your EPD speed when it has just reached ground level. So what do I know? Well, I know that it's in free fall, so acceleration is going to be negative 9.8. The time I don't know. The initial velocity is 0 because you start at rest. The final speed I need to know. The distance it falls is 2 meters. That means, right, I'm not interested in the time of the fall until part B. So I'm going to do V final squared equals V initial squared plus 2AD. So that means that I'm going to have a final velocity of, is what we're looking for. This is 0 plus 2 times negative 9.8 times negative 2 because I've fallen to the ground. So you get a final velocity of 6.26 meters per second. The second question says, find the time it takes to get to the ground. So for that, you can use any kinematics equation for this, but we can just use 6.26 equals 0 plus negative 9.8 t. So 6.26 divided by 9.8, and it's negative 626 because it's moving downward. You can't have negative time, so then you get the time it takes to get to the ground. Number 2, assume that the entire crumple zone behaves as it should, with the entire structure crashing down. Use kinematics to find the acceleration while it comes to a stop. So now we're here. So if you think about it, you've got your, I'm going to draw this in 2 stages. So here's when it first touches the ground. Now we know that this velocity now is negative 6.26 meters per second, right? So from this point down to the third stage where the pieces now look like kind of like this, right? It's all squished out to the side, right? This is position 2 and this is position 3 and this was position 1. Okay? So this now we come to a stop. So the question is now find the acceleration while it comes to a stop. So we have V final is 0, V initial for this stage is negative 6.26. We want acceleration, and we know the displacement is that 15 centimeters or 0.15 meters from here to here, right, when it squishes down from position 2 to position 3. So that's going to be the same equation as the first one, but now you're solving for A. And this is a negative displacement still. So you have 6.26 squared divided by 0.15 divided by 2. And you get 130.6 meters per second squared is acceleration. So that might seem like a pretty big acceleration, but it's, you know, it is, right? It's got a big force acting on it, so it's going to take a while to slow down. So now we want to find the force of the floor on the egg. So this is A, what we just did here, 2A, 2B is asking for the force, and net force equals mass times acceleration. So here's my egg, here's the force of the floor that I'm trying to find, here's MA. So net force equals mass times acceleration, Fn minus mg equals ma. So we have to find Fn. So the mass is 0.16 kilograms times 9.8. That came from here, right? This is 160 grams total, which is 0.160 kilograms. I did that up here. So that has to equal the mass, 0.160, times the acceleration, which is 130.6. So let's solve for that. Fn minus 0.160 times 9.8 is 1.568. And then 0.160 times 130.6 is 20.9. So add the 1.568 to the other side, and you get a normal force of 22.5 newtons. Okay, so number 3 asks you to do the same thing but use the law of conservation of energy to find the force. So let's take a look at our diagram. We have our egg carrier here, and here's the squished out egg carrier here. And this position was at 2 meters. Therefore, this position is at 2.15 meters, right, high, because this was 15 centimeters. This is our 0 position. So when we look at this, we want to know at the bottom, right, at this end point, the bottom of the egg carrier is at 0, right? So we have GPE equals work out. And so we have mgh equals the normal force times the distance. And we've got our egg, and the carrier's mass, 9.8. But now the distance is 2.15 meters because we're measuring from where the bottom of the egg carrier is all the way to the ground. Okay, that's the distance you need this time. So make sure you're consistent with this. I actually have done that wrong a couple times and had to go back and fix it. And then the distance that the floor acts is only that 0.15 meters, right, that it squishes down. So when you do this, you get 0.16 times 9.8 times 2.15. That's 3.37 joules. This is Fn times 1.15. And then you divide by 0.15 and you get 22.5 newtons, which is what we got the other method. Okay, so that's number 3. Number 4. Use the impulse change in momentum relationship to find the contact time. So this is the impulse change in momentum relationship. We now have the force. We want the contact time. We know the mass. We know that our final velocity is 0 and our initial velocity is negative 6.26. So when you do 6.26 times 0.16, this is 1.00, and you have 22.5 on this side. You get a contact time of 0.045 seconds, a very small time, of course, right? It happens very quickly, more than we can really see. Now you're asked to make a force time graph. So let's take some of this information and make a force versus time graph, or it's also called an impulse graph. So there's a couple of things that you need to be able to do. First of all, you need to be able to understand that the general shape should be like this. Okay? The contact time when it hits the floor from here to here is this time that you just solved for. So if you can make this 0 and this 0.045 is fine, right? But from the time it dropped, we already got that time. The time of the drop itself is 0.64 seconds, right? And now we know from here to here, if we make 0 time when you drop it, This is where it hits the floor. Then this should be the contact time, right? This position is the contact time. So this time here is 0.685. We just added on 0.045 seconds to this hitting the floor time. This is coming to a stop, or bouncing off, really. End contact with floor. The assumption being that it bounces up, which most of yours do. So this is not to scale, obviously. This part should be much bigger than this. But what about our force? So our maximum force that you're going to have here, this maximum force, if you track along, we didn't solve for the maximum force really, but that's this is sufficient. We have 22.5. We're going to do that in newtons. Okay, our average force would be half of that. All right, and then number 6, use the pressure relationship to find out how much pressure was exerted on the EPD. So pressure is force over area. We've got the force is 22.5. The surface area, right, because that's what this is, surface area. The surface area is going to be the base, right, the area of the base of this contraption. So if you drew it 3D, right, it would look like here's, it was a perfect square with these shapes kind of attached to it like this. This my design, whatever it is, and here's my thing. So my base is a 10 by 10 square. That's in centimeters, so 0.10 by 0.10. So this will be 0.10 times 0.10. That's my surface area. So 22.5 divided by 0.1 times 0.1 gives me a pressure of 2,250 pascals. So the remaining questions are thinking questions. So let's kind of go through those. How is the crumple zone a safety feature? And use Newton's laws to explain how the design of the base is important to save the egg from injury. So an object in motion stays in motion unless acted upon by an unbalanced force. So your egg is in motion and it needs to come to rest. And so that's the first law. And so it needs an unbalanced force. Newton's second law says that the bigger the acceleration, the bigger the force is going to be. So you want to reduce that acceleration. And in order to reduce the acceleration, you need to extend the time and or the distance of that crumple zone. The crumple zone behaves like a time extender, a contact time extender. Would it have been better to have a wider base or a narrower base? And width is good. You want to have a wider base to do this with so that you can reduce the pressure on the egg. You can distribute the force over a wider area. And last, describe the 3 collisions that occur during a collision and how they affect your egg survival. So there's 3 collisions. Your EPD with the floor, first collision. Your egg with the inside, with the floor of your EPD. And then third, the yolk with the inside of your eggshell. Those are the 3 collisions that occurred when your egg struck the ground. What I'd like you to do is try to do the same thing that we just did, but do it for a different situation where you drop it from a higher altitude and you have different dimensions so that you could try to duplicate these steps on your own.